Okay, let's start. Hi, I'm Trishanthananakar from Imperial College London. I'm going to chair this next session. Our first speaker is Damian. She's going to talk about resilience of robots, a view from inside the human body. We have 1 minute to go then, so, but you can maybe put your slides on.
Yeah, thank you, Trish. Yeah, tell me if you see the slides, please.
Yeah, that's great.
Lovely. All right. Good morning and hello, everyone from many places on the planet. Thank you so much to the organizers for inviting me. Really delighted to be here and have the chance to present some of the work we do in our lab. So we are a Sheffield Biomedical Robotics Lab at the University of Sheffield. And in this group, we develop medical devices, medical devices and implants that reside inside the body for short-term or for long-term adaptive healthcare. And so some of the things that we focus in our research is how to engineer tissue responsive interfaces, so the interface between tissue and machines in order to produce quality tissue. Also, we look at how we develop this resilience in robots such that they can really operate over a long period of time inside the body. And also how to build this kind of robot that can conform to anatomy that evolve over time or to tasks that evolve over time. So to tell you a little bit about where we are coming from, when we discuss about resilience and when we work on resilience, we, for a few years now, we've been developing implantable robots that need to stay inside the body for weeks to months. And they would regenerate tissue inside the body. They would elongate organs just by applying some gentle mechanical stimulation over that period of time. And so there are many technological challenges that go into building such implantable robots, and some of these are listed on this slide. But today I'm going to focus on the fault tolerance as a technological challenge, because as you can imagine, we cannot simply just go inside the body whenever something breaks in our robot. And so we have had some nice results and successes with our implantable robots and managed to elongate tissue. These robots were implanted in pigs, and one of those pigs is in this video here. You can also see the robot under a fluoroscopy imaging and how it gently applies that tissue traction. And after a few weeks of the robot being inside the body, we demonstrated that we were able to grow the stretched segment by 77%, which is really, really great. But we do not want to overlook those kind of initial failures that have built on which we have built the current robotic implants that we are working now. We have had various level of failures. Sometimes when after those weeks of experiments, when we retrieved the robot was almost in pieces. And so something that you can see in this picture. And things started to kind of fall down, break down from this soft encapsulation that is responsible to protect both the robot and the human body. So there is the patient risk over here that is really critical. And there is also a real socioeconomic cost to robots and medical devices really breaking down. So we really wanted to think how we can overcome the vulnerabilities of these robots and soft robots in particular, and how maybe we can even exploit these vulnerabilities in order to design smart devices. And so we took this kind of work and tried to think how we can build resilience in soft robots, and we came up with some criteria which are surely not comprehensive. We thought that the robots need to have some sort of addressability in their structure, so they need to have some cellular or modular type of structure to help us localize where things happen, where faults occur. Then we thought that these robots should also be endowed with some kind of internal state for self-identification that would characterize the robot physiologically or pathologically. And then obviously we'll need to implement those kind of mechanisms, reactive or active, that will treat the faults, respond to the resilience breaches. So we started with some soft building blocks like this device that you can see here, which is an inflatable membrane. And we thought it can find a versatile application across the fields. But here in this slide, you can see a variation of soft robots that were built by stacking and configuring these inflatable membranes such that the robots can extend longitudinally or axially, radially. They can rotate in 3D. We have seen that they have high extensibility, going up to 300%, low input pressures, and has high scalability. So the one on the right side has a 2-centimeter diameter. So coming to this internal state, we wanted to enhance the soft robot ability to know itself as a state, and we achieved this by using biocompatible ionic conductive liquid, so in a chemically modulated way. So in this way, the soft robot can self-tune either its volume or its conductivity. So here you see some examples where we control the volume of the soft robot while keeping the concentration constant. So the concentration comes from sodium chloride that is inside a soluble water solution. And then the other case where we control the concentration by adjusting the circulation of the fluid inside the soft robot. So using this technique, we ended up having this kind of soft sensor actuator where sensing and actuation is multiplexed, and we have multimodal sensing of displacement and force as a proprioceptive and exteroceptive sensing. We've characterized this soft sensor actuator in a variety of ways by looking at the internal pressure and also resistance when we applied various loads and geometrical constraint. And we've also seen that this kind of soft sensor actuator has the ability to predict the stiffness of a number of objects. And so it showed a good resolution in terms of displacement and force. And now going to the reactive response to faults and how the faults can be treated. We have developed an automatic and passive fault isolation for inflatable soft robots. And this is taking the form of a valve which exploits the burst phenomenon and the pressure gradient that is dynamically created through the burst. So this valve over here, shown from the side view, we see here the flow channel. We have another chamber on top, and there is an elastic thin membrane that separates these chambers. Characteristic that is also critical to the way it works, the valve works, is a structural constraint right here that already creates a separation between the supply pressure and output pressure. So when a burst occurs, this pressure gradient deforms the thin elastic membrane and blocks completely the flow. And so this is what you were able to see in this video, where we have a soft robot made out of 3 interconnected inflating balloons. And even if the knife pierces one of these balloons, the other 2 maintain their pressurization. And a little bit of about the active response. I know the time is ticking. This one we have demonstrated on a flexible robot platform, one that can change its shape by size elongation, by elongating its size and flexing in various directions. This is a more high-level type of response where we take readouts from force sensors and from flexible sensors in order to identify where the fault source is. But the interesting thing in this work is that we are using and we're exploiting the flexibility of this robot in order to amplify the differences between the signals in order to disambiguate the source of the fault. And then as a consequence to that, we can choose a strategy by shifting the control to parts of the robots that are still functional. So to summarize my work, the soft robotics opens up this wide pool of materials, but maybe even more interesting to the way matter can interact. And this way, I think we can achieve a better emulation of the living system, especially when it comes to resilience, but not only. And also that embodied in resilience, I think provides a pathway to a new and exciting form of adaptability and intelligence. So I want to thank all my lab members, and in particular, those that are depicted here, whose work I mentioned today. Thank you all for your attention, and look forward to get any questions later. Thank you.
Great, thank you, Dana. As usual, it's amazing. We go to the next speaker, is Etienne Berry. He is from Imperial. He's going to talk about body adaptation to improve haptic sensitivity.